Next speaker is Edgar Labarga from the University of La Rioja. Is it right? So Edgar will talk. I have not here the title. I'm sorry for that. Very good. So the talk is about discrete appeal sequences in the Dunkel Z2 context. So please, Edgar, remember to be here above the light, close to the microphone.
In the 18th century, one of the foremost problems in the theory of the summation of series was to sum the inverse of the squares of the natural numbers. That is the Bassel's problem. The history was presented in the first talk of this morning by Professor Ribeiro, but let me put my work, my talk into context by reviewing some aspects of this problem. The first one who obtained a solution was Leonhard Euler in 1734, and he proved that the sum is equal to pi squared over 6. Later on, he also proved the following two identities. The first one can be viewed as a generalization of Bassel's problem, considering instead of squaring general even power. He showed that the sum is equal to some constants times the corresponding Bernoulli number. The second one of the identities is a kind of alternating sum and is related to what are called Euler numbers. Bernoulli and Euler numbers are particular evaluations of Bernoulli and Euler polynomials. Here we have the sequence. The first one is the sequence of the Bernoulli polynomials and the first terms of the sequence, and the second one is the Euler's sequence. They have many properties, but note that if we take one of these polynomials, for example B2, and take the derivative of B2, you obtain the degree 2 times the previous polynomial of the sequence. That's an interesting property that we are going to use in this talk. So let's go back to the identities of Euler, and if you rearrange in some way the constants, you can think of that sum in a way that you are summing the inverse of powers of the zeros of the sine function. And in the second case, you have the zeros of the cosine function. Well, there is a relation between Bessel functions and sine and cosine functions. So one can think in a natural way in the following problem. Try to sum the inverse of a square of even powers of the zeros of the Bessel functions. It's a kind of generalization of Euler's identity, and this was already done in this paper by Lord Rayleigh in 1873, but he didn't obtain a connection between this series and a kind of generalization of Bernoulli polynomials, or well, Bernoulli numbers. That was done in this paper from Oscar Ciaurri, Duran, Perez, and Barona, that was published in 2018. And the idea is try to generalize two frameworks. The first one is the framework of Appell sequences. What is an Appell sequence? An Appell sequence is a sequence of polynomials, Pn, of degree n, and they have the property that when you take the derivative of any of these polynomials, you obtain the degree times the previous polynomial. You can obtain a characterization of this definition in terms of the Taylor generating expansion of a function. That is, the polynomials appear as the coefficients of a Taylor expansion of some function, the generating function, which is of the form at, it only depends on t, times the exponential of xt. Why the exponential of xt? Well, because the exponential is invariant with respect to this operator, with respect to the derivative. So, if you fix function at, you obtain a sequence of Appell polynomials. We already mentioned that Bernoulli and Euler polynomials have this property. So, if you take this at, you obtain the Bernoulli polynomials, and if you take this at, you obtain Euler polynomials. So the idea is try to generalize this definition to try to sum the Rayleigh's function. And you have to consider a kind of Bessel context, which is known as Dunkel theory. Dunkel theory was introduced by Charles Dunkel in works of in the late 80s and the beginning of the 90s, and it's related. It tries to generalize harmonic analysis in the framework of finite reflection groups. We are going to consider the most simple case, that is the group set 2. And here we have a kind of generalization of the classical derivative. That is the Dunkel operator. We have a parameter alpha that we are going to suppose bigger than -1. And the Dunkel operator is a differential operator. You have a differential part, which is the derivative, the classical derivative, and we have a difference part here. And you can see the action of the group here. Well, so if we denote calligraphical I as a kind of modification of Bessel's function, we can obtain a function which is the Dunkel kernel, and this function is invariant under the Dunkel operator. The form of the Dunkel kernel is a generalization of the classical exponential, so you consider this series and you replace the classical factorial with a Dunkel factorial, if you want. Also, we have a kind of Euler's identity with the cosine and sine. So if you replace the parameter alpha and you make it equal to -1/2, you obtain that the Dunkel operator is the classical derivative and the Dunkel kernel, or Dunkel exponential, is the classical exponential. So you are generalizing the classical context. So we have all the ingredients to try to sum Rayleigh series and try to obtain some identities in the spirit of Euler's. Let me review the Dunkel set 2 context just briefly. We have an exponential, a Dunkel exponential. If you take alpha equal to -1/2, you obtain the classical exponential. You have a kind of Dunkel derivative, Dunkel operator. You take alpha equals to -1/2, you recover you have the classical derivative. You have a gamma, which is the generalization of n factorial. And then we can define Appell-Dunkel sequences in this context. That was done in the paper that I already mentioned and in some other papers after that. So the definition is the following. You replace you have a sequence of polynomials, which depends on the degree, have degree n, and there is a parameter alpha. Take the Dunkel derivative of any of one of these polynomials, and you obtain n, more or less n, because you have an alpha dependence, but n times the previous polynomial, Pn minus 1. The same definition as in the classical case, but with the Dunkel operator. And you can give a characterization of this definition in terms of the generating function, which now has the form at times the exponential, the Dunkel exponential, the Dunkel kernel. So if you take this at, you obtain a kind of generalization of the Bernoulli polynomials, and if you take this at, you obtain a kind of generalization Dunkel polynomials. I mean generalization because if you take alpha equal to minus 1/2, you recover the classical case. So, well, we have two contexts, but we are applying an operator, the classical derivative or the Dunkel operator, in a continuous way on the parameter x. What happens if you take a difference operator in a discrete case? You can define Appell sequences in this discrete case. So you define a discrete Appell sequence as a sequence of polynomial of degree n, and when you take the forward difference of these polynomials, you obtain the degree times the polynomial of degree n minus 1. You have also a characterization, and now the function that appears, the generating function, has the form at times the function that which is invariant with respect to this operator. It is a kind of exponential function, and when you take at equals to this, you obtain the discrete analog of the Bernoulli polynomials, which are called Bernoulli polynomials of the second kind. And if you take this one, you should obtain the Euler's polynomials of the second kind, the discrete analog of Euler's polynomial, which are not called in this way in the literature, and the name is Boole polynomials, but they are the discrete analogs of Euler's polynomials. So our aim was try to generalize this discrete context to the Dunkel case, to the Dunkel context. So we almost did it in this paper of 2022, and in the following one also in 2024. So the natural idea is take an operator which is a generalization of the forward difference. Well, there is a Dunkel translation in the Dunkel context, which is a generalization of the classical translation. The definition is the following. The classical translation can be viewed in terms of the Taylor expansion where you have the derivative. So replace this derivative with the Dunkel operator. So you obtain the Dunkel translation. That it is a much more complicated operator, but and has this property. If you take the translation of the Dunkel exponential, you obtain the product of two exponentials. Well, the idea is try to replace this forward difference with a kind of a generalization in the Dunkel context. So the most natural one, I think, is try to replace this term with the Dunkel translation by 1. Well, that problem, we are not able to solve that problem. If we consider this operator, we cannot obtain a function that is invariant under this operator. So we need to replace the forward difference by a central difference. Okay, we are not able to do this in this case, so we are going to take the central difference. If we define a central discrete Appell sequence in this way, you have a sequence of polynomials of degree n where you take the central difference instead of the forward difference, take the central difference and define the discrete central Appell sequences. In this way, you can characterize them in terms of a generating function of this form. This function is invariant under the central discrete difference. So the idea now is to replace this operator with this operator, a central difference in the Dunkel context. And now we can find the function that is invariant under this operator. What is that function? So we have to replace this by a function that is invariant under this operator. We thought that maybe if in this case the function is of the form an exponential of x times some function that depends only on t, maybe in the Dunkel case is the same. So we thought in that. Try to put here an exponential of x time, Dunkel exponential of x time a function that only depends on t, ht. You have to find ht. And if you make the computations, you obtain a function, this function g of h. So ht must be the inverse of this function gt. Then we can define the discrete Appell Dunkel sequences in the following form. You define them considering the central Dunkel difference operator, but the important part is the characterization of this definition. The generating function has the form at times the exponential of x times a function that only depends on t, and that function is this one, the g inverse. If you take alpha equals to -1/2, you obtain the inverse of the hyperbolic sign. Well, so in this framework, we could define the analog in this discrete case of the Bernoulli polynomials, which are we called Bernoulli-Dunkel polynomials. You have to take this at, and if you take this at, you obtain the Boole-Dunkel polynomials, the analogs of the Euler of the Boole polynomials in the discrete case. Here's a brief overview of all what we have, which is the classical case. Bernoulli polynomials are Appell sequences because of these relations, and has this property. In the discrete case, the properties intertwine. So the Bernoulli polynomials of the second kind are Appell discrete because of this, and now they have this property. In the Dunkel case, you replace this derivative with the Dunkel derivative, and you obtain n times this, and they are Appell Dunkel sequences. And our contribution was to define the Bernoulli polynomials of the second kind in the Dunkel context. They are Appell discrete because of this relation, and they satisfy some properties. Now here, this is a central falling factorial, but it doesn't matter. And in the Euler or Boole framework, instead of the forward difference operator that we had in here in the Bernoulli polynomials, in the property of Bernoulli polynomials, we have a kind of mean operator, but the relations are more or less the same. So I think that it is time to thank for the invitation to the organizers, and especially to Kenier. And well, congratulations for the conference to all of you, and thank you for your attention. That's all.
Thank you, Edgar, for the presentation, for the clear presentation. So it's time for questions or comments. Yes, please.
Thank you, Edgar. Very nice talk. I have a question concerning the evaluation of the reciprocal powers of the zeros of the Bessel function. Does that, in that evaluation, the analog of Euler's formula, does that appear your analog of the Bernoulli polynomials?
Sorry, can you repeat it?
You
mean the Rayleigh function? Yeah.
Yes.
Yeah,
If you take this, that series,
this one?
okay,
okay,
you get an analog of Euler's formula somehow.
Yeah, sure.
And
sure.
the Bernoulli numbers that appear in this formula, the analogs, are the same as that you got in the Duckle context?
You mean we have here? They have, because I don't have. They have an analog of the Euler's identity.
Yeah,
okay, they have numbers of Bernoulli numbers. But they are not the same as the evaluation of in the discrete case. No, okay, they are not the same. Okay. They are not the same. You have some polynomials in the continuous case, generalized polynomials in the continuous case, and we have other polynomials in the discrete case. And they are not the same.
Okay, and can you relate with some kind of series analog of the zeta?
Yeah, I think so. I think we have some properties that relate the continuous and the discrete case.
Oh, that's nice.
Yeah, I think so.
But do you have a paper or is still work in progress?
Excuse me?
Do we have a paper?
Yeah.
Okay.
I can send you the paper if you want.
Okay, perfect. Okay, so, thank you.
Are there any other questions? Yes, wait a moment.
Thanks for your nice presentation, and I would like to know if, for example, you can extend this to the what we call the Q-Dunk operator.
Yeah, there are some works in this line of research. You can define the Appell-Dunkel sequences to that context of Q theory. Yeah, yes. There are some works in that line, but in the discrete case, I haven't seen anything about that. In the continuous case, yeah, you can, there are some works, okay. But in the discrete case, I haven't seen that.
Okay, thank you.
But that's a really interesting question.
Okay, thanks. Because I remember that I saw, when I saw that operator, I remember that there is also an operator called Q-Dunk operator.
Yeah, sure.
It's for the discrete case.
Dunkel operator is a special case of a certain Q operator. And it can be generalized to the Q-Dunkel Q theory. Yes. There is some literature in this line.
Okay, yeah. Yes. Please, the last question is like, when you are talking about the Appell polynomials, yes, can you consider the orthogonality there?
You can, but we haven't thought about that. Okay. Yeah. But it is an interesting. This is an interesting question. Also, the orthogonality. Which polynomials are orthogonal in which Appell polynomials are orthogonal?
Yes.
That's an old question in the classical case, but in the Dunkel case, I don't know anything about that.
Okay. Thank you. Thank you.
Thank you. Are there any other questions? No, very good. Let's thank both speakers again.
Thank you.